Assalamu alaikum wa rahmatullahi wa barakatuh. So today we are going to discuss about the effect of feedback on the bandwidth of the amplifier, of the effect of feedback on the bandwidth. That's enough. Okay, so what is bandwidth? So I can write my bandwidth as BW. Okay, so I will be using this notation. Okay, BW is the bandwidth. Okay, bandwidth. So what is bandwidth? So if you take any operational amplifier and if you give some voltage, so if you take any operational amplifier and give some voltage, let's say you are giving something here, very small voltage, then this voltage is having some frequency, so you are increasing the frequency. For example, like this, say let's say this is having some frequency, some 100 hertz, and this is having frequency 200 hertz, and let's say this is more frequency. Like this you are doing. Now the gain of the amplifier, so you are measuring the output also. Then what is the gain of the amplifier? The gain of the amplifier can be written as gain is equal to output voltage amplitude divided by input voltage amplitude. But you can see that this gain is not fixed. The gain is not fixed as you change the frequency. So when you change the frequency, the gain also will change. That means that up to some particular range of frequency there won't be any significant change, but after some frequency you can see that the gain will be changing. So I can rewrite my gain actually as a function of frequency. My gain can be written as a function of frequency. That means it is nothing but the voltage V of t with some frequency f divided by V in, which is a function of frequency. Actually this is V out of t and V in of t. So this is having some frequency, this is having also some frequency. So I can say the gain is a function of frequency. So the gain will be usually following a pattern in most of the devices. If you change the frequency, the gain will be changing, like something like this. That means the gain will not be, for suppose f equal to 0, f means actually the frequency. Okay, if f equal to 0, you will be getting some maximum gain and it will be continuing like this. But after some range you can see that the gain is decreasing. Okay, so the gain is decreasing. So this kind of phenomenon you can see in most of the devices, and here also in operational amplifier. So in op amp, I am saying in op amp, in open loop without any feedback, that means open loop, the gain, suppose it is changing like this, the gain I will call it as open loop gain, AOL, and you can see that this AOL is a function of frequency. So the open loop gain is a function of frequency. Okay, frequency, and the closed loop gain will also be the function of frequency anyway. So you can see here that maybe this may be 0 hertz and this can be something like maybe 10 hertz, maybe 100 hertz. I am using some logarithmic scale. This is 1000 hertz, maybe 10,000, like this it is going on. Okay, 10,000, 10 power 5 anyway, this is 10 power 5, and this may be 10 power 6 or 1 mega. So you can see that at some point, up to some point, the gain is constant, and after this particular range this gain is actually start reducing. So this is a critical point So this point is a critical point. So the frequency at this critical point can be given by using this number here, and this frequency we will call it as the cutoff frequency. And since this is start decreasing here, and this is the upper and higher value, this is nothing but the upper cutoff frequency, and usually it is denoted by FCU. So what is FCU? FCU is the upper cutoff frequency. It is the upper cutoff frequency. Okay. And how you will be selecting this point? Suppose so the gain at this area, actually at the initial stage, we will call it as the mid-range gain. So what is this gain? This is the mid-range gain. Okay, mid-range gain. So this is nothing but the mid-range gain. So the FCU is also known as FC. There is another notation, both are same in a way. Okay, same. In some textbook you can see it is FC also. And this is the lower, actually you are starting the frequency from 0 here. So this is the lower part. So this we will call as lower cutoff frequency. But in this case it is 0. In some okay, in this case it is 0. If you are designing a filter, then it will be different. If you are designing a band pass filter, then lower cutoff frequency will not be 0. Okay, but in this case, in the natural response of the amplifier op amp, actually it will be like this. Now this frequency we will call F lower cutoff, FCL. Okay, that means FC4 cutoff and L4 lower, and here you see FC4 cutoff and U4 upper. Okay, so we have FCL, it is the lower cutoff frequency. Okay, frequency. And this gain, I told you, the gain, the part where the gain is constant, so that is nothing but this part actually where the gain is constant, that I told you, this is nothing but the mid-range gain, and this is usually represented by open loop for mid-range gain. And the gain at this area, that means the gain is changing. So in the mid-range gain means almost it is constant up to some level, and the gain at this point, that means the gain during the slope, actually during the slope part, actually it is given by as AOL, the open loop gain, as a function of frequency. You see it is a function of frequency, or simply we will say AOL also. It is given as AOL in the mid-range gain, that means this one, this is AOL mid, divided by square root of 1 plus F square by FC square. Okay, so this is the formula for finding the frequency, the gain at other points. Okay, so this is the formula for finding the gain at other points. Now we will see what will be this is FCL. Okay, not L, it's upper cutoff frequency, so it's FCU, upper cutoff frequency. Now we will see this formula more detailed. AOL, okay, I am talking about this area. So the gain at these points, that means after FCU, this is the frequency F, and this is the gain, open loop gain. So AOL will be equal to AOL mid divided by square root of 1 plus F square by FC upper cutoff frequency, the whole square. So if the frequency, that means this is the complete frequency axis, you know, this is the frequency axis. If the frequency is less than FCU, the gain will be approximately equal to AOL mid. Okay, always it will be AOL mid. That means this gain, I am saying it is AOL mid-range gain. But if f is greater than or equal to FCU, then the gain AOL is equal to, here also you can say it is gain, same thing. Here gain means AOL, okay, and here the gain AOL is equal to AOL mid, that means the mid-range gain. So what is mid-range gain? The portion where the gain is constant, that is the mid-range gain, okay, divided by 1 plus f square by FCU square. Now what will be the gain at what will be the gain at f equal to FCU? What will be the gain? So AOL for f equal to FCU is equal to AOL mid divided by square root of 1 plus FCU divided by FCU square. So this is equal to AOL mid divided by 1 plus FCU square divided by FCU square is 1. So it becomes the square root of 2. So this is very, very important notion. Why I am considering like this? You see, why I am considering like this cutoff frequency. So what is the cutoff, what is the gain at cutoff? AOL at f equal to FCU is equal to the mid-range gain. Mid-range gain is the maximum gain. That means this is the maximum. You see, this is the maximum and this is the cutoff. And what is the gain here? That's what we are going to see. So what is the gain here? That is the formula. It is AOL made divided by square root of 2. Now that means that what is the gain? Basically you should understand what is the gain. You know that the gain is equal to output voltage divided by input voltage, okay. So this is the gain. So at input voltage, actually you are not going to change, only you are going to change the frequency. Am I correct? Yes. So you are going to change only the frequency. So the magnitude will be for the input voltage will be same. Magnitude for the input voltage will be same, and you vary the frequency. So what will happen? The output voltage will also change according to the frequency. So for mid-range, actually you will be getting maximum output voltage, but after some frequency, that means FC, upper cut of frequency, you will be getting you will be getting a gain which is start decreasing. That means the output voltage will be start decreasing after this point, okay. Now what will be the magnitude of the output voltage? So at mid-range, what is mid-range? Mid-range means this portion, okay. At mid-range, V out is V out mid-range maximum, and at upper cutoff, what is mid-range? What is mid-range? What is the voltage? V out will be equal to, at f equal to FCU, it is nothing but V out mid, okay, it will be equal to V out at FC equal to f equal to FC, FCU is equal to V out at mid-range divided by square root of 2. That's why you are getting the gain also as a square root of 2. That means that the voltage at critical frequency will be 1 by square root of 2 times 1 by square root of 2 times. So we can conclude that, so the voltage at at critical frequency at f equal to FCU is 1 by square root of 2 times voltage V out maximum, or we can say it's a mid range. Okay, same, both are same. Okay, so what will be the power? Then the power, you know that then the power at F equal to FCU will be, you know that power equal to voltage square. So if the voltage is 1 by square root of 2 times the maximum, the power will be P out maximum, or at mid range you have a power, then it will be 1 by 2 times the power at the mid range. Am I correct? Because power equal to voltage square. That means that if you consider this area, you have a maximum power here, P out maximum here, and at critical frequency F equal to FCU, you have a power, that means it will be half of the P out maximum. Okay, this P out maximum I can call it as mid also, both are same. Okay, so maximum, or I can say mid. Okay, or mid I can say. Okay, both are same. So you can see here that I will get the maximum power here, and here the power will be maximum by 2. So I am actually allowing the power to go from minimum some up to maximum by 2 is okay. Suppose you are having 100 milliwatts at the output during the as the maximum, then at F equal to FCU you will be getting 50 milliwatts. Okay, and beyond that limit it is not so good anyway. So I am considering the range of these frequencies. I am considering this range of these frequencies, and I told you this is the lower cutoff frequency, the range of this frequency. That means this is FCU, this maximum frequency, this is the maximum frequency, and this is the minimum frequency. Okay, minimum frequency is a maximum frequency. Okay, and the minimum frequency. So FCU minus F's lower cutoff frequency, this we will call as the bandwidth. Okay, and another notation for this is BW. Okay, so bandwidth is given as FCU minus FCL. In our case, so this is the gain basically. So in our case, our bandwidth will be equal to, in our case, open loop op amp configuration. So in our case actually open loop op amp configuration, open loop op amp configuration, the bandwidth, okay, bandwidth is equal to FCU. By why? Because in our case this guy FCL is lower cutoff frequency, it is equal to 0 hertz. That's why. So our bandwidth is FCU, right? So this is the AOL mid-range gain basically, and this is the AOL, which is given as AOL mid divided by square root of 1 plus F square by FC upper cutoff the whole square, upper cutoff square. Okay, F square CU. Okay, so this is the concept of the bandwidth in the open loop. Okay, but when you connect the op amp in closed loop, it can be proved that, anyway I am not going to prove. Suppose you have, I will first draw the open loop configuration using this green color. I have, first of all I will draw the axis. So this is the frequency, and this is the gain. The gain can be open loop and closed loop. Okay, I will first show the open loop. So this is my open loop gain. It's going like this. Okay, this is my open loop gain, and this is my F upper cutoff frequency, in open loop. Okay, this is my open loop and this is my lower cutoff frequency, and which is in open loop. Okay, open loop, both are in open loop. Okay, now open loop, and this is my open loop. This is the cutoff frequency, and this is my open loop mid-range gain. Okay, and this can be given as AOL divided by square root of 1 plus f square by f upper cutoff the square. Okay, so this is my formula. Now you can see something very interesting thing, that you will be getting after. So this is with so all these are actually showing in open loop, open loop. Okay, now we are going to connect the op-amp in a feedback. A feedback can be a negative feedback. Okay, now after feedback, so this green color, actually I will write it, green color is showing the open loop. Okay, now I am using the red color, this is nothing but the closed loop. So you know that the bandwidth was what was the bandwidth in open loop? In open loop the bandwidth was this much. So what is the bandwidth? The bandwidth was FCU open loop, right? This was the bandwidth. So the bandwidth in open loop was FCU open loop. Okay, now when I connect in closed loop, actually it can be proved that the bandwidth in closed loop will be equal to bandwidth in open loop. So I will write this as open loop also here, that will be avoiding the confusion. So bandwidth in open loop, bandwidth in closed loop will be equal to bandwidth in open loop multiplied with 1 plus B into AOL mid. So you can see that what is this B? B, you know, it is nothing but Ri divided by Rf plus Ri in our feedback coefficient. Actually this is B, you know this. So this is the feedback coefficient. So what will happen? The gain of the op-amp, you know that when I connect the op-amp in feedback, the gain of the op-amp will be reducing, but the bandwidth will be increasing. You see here that previously the gain was very high. You know, this was the gain in open loop gain, that means AOL mid. Now a closed loop mid-range gain will be lesser than that of AOL mid. It is because I told you when I connect the op-amp in feedback, we can control the gain. So we will not be using the gain of 10 power 6 or 10 power 8 like that. We will be using a gain of 100, 200. So gain is reduced. But what will happen if you connect this like this? It is meeting at some point here, and you see here that this is now your new cutoff frequency. New cutoff frequency will come here. So this is now the new cutoff frequency. This is nothing but FCU in closed loop. So what happened? The overall bandwidth of the op-amp is now this much. So this is the bandwidth. This is the bandwidth in closed loop. So the closed loop response has given you a large bandwidth. Now we will see what is the area under these curves. Okay, what is the area under this curve? So you see here that there is an area. You can say, you can consider this area up to this. Okay, you can see for the open loop case you have an area because you have something like this, and this is the starting point of decreasing, the point where the gain is decreasing. So you can see here that there is an area here. What is that area? Is approximately avoid this bend anyway, we can approximately write this area as AOL mid multiplied with your FCU, because here it is FCU, the frequency is FCU. So that is approximately the area FCU in open loop. Okay, this is the open loop. So area in open loop. Okay, now we will see what is the area in closed loop. In closed loop, the area is, you see here, it is going here up to this and going down, right? So the area, you can say that the area is this much, right? This is the area. So what is this portion? You see this width is AOL mid, and this width is FCU closed loop. So the area in closed loop is equal to A closed loop mid multiplied with FCU in closed loop. Okay, and we will call this both as, you see, this is the gain and this is the bandwidth. Okay, whatever be closed loop or open loop, this is the gain, this is the bandwidth. Okay, so this is nothing but gain, both are actually, this is also gain and this is the bandwidth. So this is nothing but gain multiplied with the bandwidth, right? That means we can say that it is nothing but gain bandwidth product, right? And it is an inherent property that the gain bandwidth product, the gain bandwidth product in open loop will be equal to the gain bandwidth product in closed loop. In closed loop, I can say like this, in closed loop. So your area, so I can say that my area area in open loop will be equal to my area in closed loop. So I am going to derive a very important notion, that means that AOL mid into FCU in open loop will be equal to a closed loop mid into FCU in closed loop. So this is very important formula. Okay, this is very important formula. So I hope this is clear to you, right? Now okay, so that's it. I think this is clear to you. So what is bandwidth and what is the notion of bandwidth, what is lower cutoff frequency and what is upper cutoff frequency. Now we will see representation of the frequency response in decibel. You know that usually the voltage gain in dB is equal to 20 log voltage gain divided 20 log voltage gain, right? And what about the power gain? Power gain in dB is equal to 10 log power gain, right? So this is how you can convert the into dB. So for if you are using power, you have to just use only 10, but in voltage gain you are using 20. Why? Because voltage is nothing but, because power is equal to voltage square. Okay, so in power already you are considering that square. Okay, and now we will see how we can represent the gains in dB. Suppose you have, this is the frequency. So let's say I am considering the open loop case. So this is the critical frequency FCU, okay, and this is the AOL mid range. Now I am saying this is in dB, okay, in dB. Now what will be this point? I told you what will be this point, the gain AOL. At this point I told you it was in dB. Is it in dB? No, we don't know, no idea, because AOL is equal to AOL mid, which is not in dB. Here this is not in dB, okay, it is not in dB, divided by square root of 1 plus f by FCU, f square by FCU square, okay. So it is nothing but, I told you at this point you have, I told you have the gain actually AOL is equal to AOL mid divided by square root of 2. So I am going to change the voltage gain into dB. What will happen now? So at critical frequency, at f equal to FCU, okay, at f equal to FCU at critical frequency. So AOL at f equal to FCU is nothing but AOL mid divided by square root of 2. So what is in dB? I will just take to convert into dB 20 log AOL at f equal to FCU, and this is equal to 20 log AOL mid divided by square root of 2. So this is nothing but 20 log AOL mid minus 20 log square root of 2. So this is nothing but AOL mid in dB minus 3. That means that this number you will get it as 3, okay, this like 3 dB. So this is the equation for AOL in dB at f equal to FCU. So same for closed loop gain also. Also a closed loop in dB at f equal to FCU is nothing but a closed loop in dB at mid range. Okay, this is both are in mid range. So this is not in mid range. This is in mid range minus 3 dB. So these are the formula. Okay, you can start. So what is that? Actually, I will represent it. This is your frequency and this is your open loop, and this is the gain I am saying. So I am talking about the open loop gain. So AOL made in dB I am saying. So everything is in dB axis now. Okay, now start decreasing. Okay, start decreasing, and this is your cutoff frequency FCU in open loop. Okay, the gain at this point, the gain here, and what is that gain? I can say this is same as this point is same, like this is the gain. And what is the gain? It is AOL mid minus 3 dB. Okay, that's it. Now for this is the case of the open loop. Okay, open loop. Now for the closed loop I will use different color. It is going like this. Okay, going down, and this is FCU in closed loop. Okay, closed loop. And what is this point? This is nothing but AOL. This is AOL made in closed loop. Okay, this is in closed loop, and the previous one was in open loop. So AOL, not AOL, this is ACL. So I have already denoted closed loop, no need actually. So this is was AOL. Okay, now a closed loop made is minus 3 dB. So what is this gap? Actually, basically this is 3 dB. It's showing actually half of the power is the point at which half of the power. So this is half of the power, half power of maximum value. Okay, and this is also half power of the maximum value, and this difference is 3 dB. Okay, I hope this is clear to you. Now I can say my bandwidth for the open loop case. This is my bandwidth for open loop, and my critical frequency is here, and this is my bandwidth for the closed loop. Okay, so with this I finish everything, the notion of the bandwidth in open loop and closed loop. And there is one more thing, okay, unity gain bandwidth. So there is one more thing which is known as the unity gain bandwidth, another concept. So I will use the next page. So the concept of unity gain bandwidth. Okay, so unity gain bandwidth. So unity gain means what? So if gain is unity, suppose gain equal to unity, and what is unity? Unity means it's 1. Okay, 1. What is 1 here in dB? So gain in dB I can say is 20 log 1, and log 1 is actually 0, so this becomes 0, so 0 dB. So both are same, both are equivalent, both are equivalent. Okay, so that means 0 dB means basically you are talking about 0 dB means you are talking about unity gain. Now I told you the gain into bandwidth will be always constant. Okay, the gain into bandwidth will be always constant. Now with this notion I can say that if I know the unity gain bandwidth, suppose the unity gain bandwidth is usually designated as unity gain bandwidth is usually denoted as FT. Okay, that is the notation for unity gain bandwidth. So unity gain bandwidth means what? The gain is unity and the corresponding bandwidth is FT. Okay, so if I talk like this, then this is the unity gain bandwidth. This gain is equal to 1, and corresponding value of FT is corresponding value of the critical frequency is FT. So I will just assume that my gain is equal to 1. Okay, so what is the unity gain bandwidth here? The unity gain bandwidth is nothing but FT. That's the unity gain bandwidth. Now we will see but I told you that unity gain bandwidth, the product of gain and bandwidth in open loop will be equal to the product of, that means the gain bandwidth product will be in open loop will be equal to gain bandwidth product in closed loop. Okay, so this is an important notion. It will be useful for solving the problems. Okay, so unity gain bandwidth means basically when gain become unity 1, so this point will be 1 by square root of 2 basically. Okay, 1 by square root of 2. So when the gain equal to 1, how much it is taking the bandwidth? Okay, that's it. That is the unity gain bandwidth. Or at 0 dB, how much is the bandwidth? So if I am having 1 is in unities in dB scale, and suppose this is the gain. Okay, so the gain equal to 1, and it is intersecting at this point FT. Okay. Now this is the gain. Now if I am representing my gain, which may be closed loop gain or open loop gain, whatever it may be. Okay. So this is showing, let's say this I am using different color. This is 0 dB. In 0 dB, this is in 0 dB. This is dB scale. Okay. So this is 0 dB. So it will be start reducing like this. So at some point this is FT. Okay. Both are same, equivalent. Okay. Now we will see some problem, then the concept will be very clear to you. Okay. So problems. You have an open, you have an a certain op-amp has open loop. Okay, open loop, that means this is open loop. Okay, open loop, mid-range gain of 1 lakh, sorry, it's 150,000, sorry, it's 150,000. Okay, and an open loop 3 dB. So what is that 3 dB? It is the critical point. Okay, dB bandwidth of 200 hertz. The attenuation, that means the B of the feedback loop is 0.002. What is the closed loop bandwidth? So I told you that the bandwidth will be increasing. And what was the formula that we have seen for the bandwidth? We have seen one formula for the bandwidth, basically. This was the formula that we have seen for the bandwidth. Okay. So in closed loop, basically you will be getting bandwidth in open loop into 1 plus B into AOL made. Okay. But you should be very careful. This should not be in dB anyway. So it has been given that the 3 dB bandwidth. So I am going to write the first, I am going to write this question. So before that, you see a certain op-amp has a mid-range, the certain op-amp has a mid-range gain of 150,000. So the mid-range gain was 150,000, it's very high, and 3 dB bandwidth. That means 3 dB bandwidth means it is showing the critical frequency. So 3 dB bandwidth means it is showing 3 dB down. So but actually this gain is not in dB, even though we will be using this terminology of 3 dB bandwidth, which is 200 hertz. That means upper cutoff frequency, FCU, which is equal to 200 hertz. Now you got the open loop bandwidth. Okay, so you have now open loop bandwidth as 300, because which is equal to nothing but your FCU, upper cutoff frequency, and the AOL mid-range gain is 150,000, right? Now you can find the closed loop bandwidth. Bandwidth in closed loop is equal to bandwidth in open loop multiplied with 1 plus B times AOL made. Okay, so this is nothing but 200 multiplied with 1 plus, so this is in hertz, basically 200 hertz multiplied with 1 plus B is equal to 0.002. It has been given in the question. The feedback is actually 0.002 into 150,000. Okay, that's it. So you will get this as 60.2 kilohertz. Okay, so I hope this problem is clear to you. Okay, and what will be the it is not asked anyway, what will be the closed loop gain? The closed loop gain will be open loop gain. So closed loop mid-range gain will be equal to open loop mid-range gain divided by 1 plus AOL B into AOL mid-range. Okay, you can calculate. This is 150,000 divided by 1 plus 0.002 multiplied with 150,000. So this will be the closed loop gain. Okay, anyway it is not asked. Okay, so we need to find only the bandwidth in closed loop. Okay, that's it. Now next question. Determine the bandwidth of each amplifiers in figures below. So this is the question number 2 and the previous one was the question number 1. Okay. Okay, figures below. Both op amps, that means in both figures actually they have used the same op amps, have an open loop gain of 100 dB and a unity gain, please note this carefully, unity gain bandwidth, that means it is known as FT, of 3 megahertz. Okay, so it is talking about the open loop. Okay, open loop. Now the first circuit is given, which is an V in, and this is RF, and this is RI, and RF is 220 kilo ohm and RI is equal to 3.3 kilo ohm. Okay, and this has been connected. So this is a non-inverting amplifier basically. So first we will solve this, and after that we will solve the next problem. So from this question itself I can easily find what is my B. What is my B here? B is equal to, is it required? So we will see whether it is required or not. It has been given a lot of things like the open loop gain of the amplifier is 100 dB and the unity gain bandwidth is 3 megahertz. Okay, so we have to find determine the bandwidth of each amplifier. So we have to find the bandwidth of each amplifier. So unity gain bandwidth has been given. Answer: unity gain amplifier, so unity gain bandwidth, which is nothing but FT, is given as 3 megahertz. So this is given in open loop. Actually basically it is talking about the open loop. So the open loop gain of the op amp is 100 dB and unity gain bandwidth is 3 megahertz. So this is in open loop basically. So unity gain means what? Gain is equal to 1, that is the meaning, and I told you gain bandwidth product will be always constant. So gain in open loop into bandwidth in open loop will be equal to gain in closed loop multiplied with bandwidth in closed loop, right? And here it has been given that this gain is 1 and the corresponding bandwidth is FT. So this gain is 1 into this corresponding open loop bandwidth is given as FT, which is equal to gain in closed loop means what? It is the closed loop gain multiplied with closed loop bandwidth. So we need to find only the question is to find the bandwidth of the amplifier in closed loop. Actually, amplifiers in the figures, and the figures are in closed loop. So basically you need to find the closed loop response. So we want to find the closed loop. So bandwidth in closed loop is equal to 1 into Ft divided by the closed loop gain, right? So this is the formula now we are getting. So what is the closed loop gain for this particular op amp? The closed loop gain is equal to, I told you this is a non-inverting amplifier, this is a non-inverting amplifier. So the closed loop gain, you know that it is 1 plus Rf by Ri. So this is equal to 1 plus, what is my Rf? Actually 220 divided by 3.3 kilo ohm, which is equal to 67.7. We got it. Now bandwidth in closed loop is equal to 1 into Ft is Ft divided by 67.7, which is equal to 3 megahertz divided by 67.7, which is equal to 44.3 kilohertz. So I do not have space here. So this is 44.3 kilohertz. So this become 3 megahertz divided by 67.7 become 44.3 kilohertz. Okay, that is the answer for the first part. Now the second part of the question, that is the part B of the question. Another circuit is given, you have to find the same thing, but this is an inverting amplifier. So 1 kilo ohm, this is your Ri, and this is the input here, V in, and this is Rf, which is equal to 47 kilo ohm, and this is the V out. Okay, now what is the gain of this amplifier? The closed loop gain, we can easily find it. The closed loop gain for this amplifier is equal to minus Rf by Ri, which is equal to 47 kilo ohm divided by 1 kilo ohm, which is equal to minus 47. So this is the closed loop gain. Okay, we got the closed loop gain. Now I told you the same formula that we have used here, the same thing. So bandwidth in closed loop is equal to 1 into Ft divided by the closed loop gain. So what is that? Ft is 3 megahertz divided by the closed loop gain is 47 minus 47. But you know that the bandwidth, actually we will not consider the sign. So I will just take the magnitude of this. So you will get here as 63.8 kilohertz. Okay, so that is the bandwidth in closed loop. So this is for the inverting amplifier, and this one is for the non-inverting amplifier. Okay, I hope this problem is clear to you. There is one more problem, that's what I am going to discuss now. One more problem. Determine the open loop gain for the following values of f. Assume the cutoff frequency or FCU at open loop is equal to 100 Hertz and the mid-range gain at open loop is equal to 100,000. Okay. Now the first part of the question is at f equal to 0 Hertz. What is the gain? We know that the formula is AOL is equal to AOL mid divided by 1 plus f square by FCU square, right? Square root of this. So this become 100,000 divided by square root of 1 plus 0 square by FCU square. This become 100,000. Same. Next, the second part of the question. So this I will write the answer here itself. So these are all the answers. Now the second question, it's at f equal to 10 hertz. Anyway, you will get something like this. AOL. This is at now 0 hertz. So this is 10 hertz. Same thing. 100,000 divided by square root of 1 plus 10 square divided by what is FCU? It is 100. So 100 square. So you will get this answer as 99503. Almost the same. Near to very close to this. Next is C, AOL at f equal to 100 hertz. That means at critical frequency. So it's become AOL is equal to 100,000 divided by square root of 1 plus 100 square by 100 square, which is nothing but 100,000 divided by square root of 2, which is you will get it as 70.710. Okay. Next, last one, D. Okay, at f equal to 100 hertz. Okay, so what is that? This implies AOL is equal to 100,000 divided by square root of 1 plus 100. This is 1,000. 1,000 divided by square divided by 100 square. So this become 9950. So these are all the different range. I can now plot it anyway. In the question it is not asked actually, I will show you how to plot it. This is the frequency f, and what is the critical frequency in the question? It has been given as 100 hertz. This is the critical frequency. So this is the critical frequency 100. Okay, I will just show it a little bit here. So 100 hertz, and I will show a little bit. This is the 100 hertz, and usually and this is 0 hertz, and this is your 10 hertz, then this may be your 1000 hertz. Okay, and like this. Okay, now we will see what is the gain here. The gain was decreasing, and it will be going like this. Okay, it will be going like this. So this is the actual situation. I have drawn not a straight line, but I have drawn something a curved line. This is the actual situation, but actually what I have told you is something an approximation, okay, for easiness. You see here I have shown everything as a straight line. It is for the easiness I am assuming like that. Okay, actually that is the relation is like this. So this gain is 100,000, and at 10 hertz, what was the answer? At 10 hertz you got the answer 99503. So the gain at this point is 99503, and at 100 hertz you have something here at 100 hertz. This point is how much? So yeah, 70,710, and at 1000 hertz you are getting as 9950. So I will use a different color. So you will be getting this point as 9950. So this is the gain, but these gains are not in dB. If it is in dB, you will not get this much big numbers. Okay, usually in dB it will be like 100, 50, 80 like this. Okay, small numbers. So this is the actual frequency response of this amplifier. Okay, now we have different types of amplifier that we will discuss in the next lecture. Thank you.